Tonight we explore one of the most unsettling mysteries in all of science. There are 200 billion trillion stars in the observable universe. Most of them have planets. Billions of those planets sit in the habitable zone where liquid water could exist. Billions more have the right size, the right chemistry, the right conditions for life to emerge. The universe has had 13.8 billion years for that life to evolve intelligence and build civilizations. Yet when we point our most advanced instruments toward the cosmos and listen, we hear nothing. No radio transmissions, no signs of engineering on cosmic scales, no evidence of intelligence anywhere except right here on Earth. Complete silence. By the end of tonight, you will understand why this silence might be the most terrifying discovery in human history. Let us start with what we know. The universe is vast beyond human comprehension. Our Milky Way galaxy alone contains somewhere between 100 billion and 400 billion stars. Each one is a potential sun that could have planets orbiting it. And the Milky Way is just one galaxy among an estimated 2 trillion galaxies in the observable universe. Do the math and you get a number so large it becomes meaningless. There are roughly 200 billion trillion stars in the observable universe. That is a 2 followed by 23 zeros. And we now know that planets are not rare. The Kepler Space Telescope revolutionized our understanding when it showed us that most stars have at least one planet. Many have several. Rocky planets similar to Earth appear to be common, not exceptional. Planets in the habitable zone, the region around a star where liquid water could exist on a planet's surface, are abundant throughout the galaxy. Conservative estimates suggest there could be tens of billions of potentially habitable planets in the Milky Way alone, and there are 2 trillion galaxies. Given these numbers, the question is not whether life should exist elsewhere. The question is, where is everybody? This is the Fermi Paradox, named after physicist Enrico Fermi. During a lunch conversation in 1950, Fermi was discussing the possibility of extraterrestrial life with colleagues at Los Alamos National Laboratory. They were making rough calculations about the probability of Earth-like planets, the probability of life developing, the probability of that life becoming intelligent. The numbers suggested that intelligent life should be common. At some point in the conversation, Fermi reportedly looked around and asked a simple question. Where is everybody? The galaxy is 13.6 billion years old. Our solar system is only 4.6 billion years old. That means there were billions of years before our sun even existed, when other stars and planets were forming. Some civilizations could be billions of years older than us. If even a tiny fraction of those civilizations developed space travel, they would have had enormous amounts of time to spread across the galaxy. Even traveling at a fraction of light speed, a civilization could colonize the entire galaxy in just a few tens of millions of years. That sounds like a long time, but it is nothing compared to the age of the galaxy. So where are they? We have been listening. The search for extraterrestrial intelligence, known as SETI, has been scanning the skies for radio signals since the 1960s. Radio telescopes around the world point at different stars and different regions of space, listening across a wide range of frequencies for any signal that might indicate intelligent origin. Artificial signals would have characteristics that distinguish them from natural radio emissions. They might have narrow bandwidth confined to a very specific frequency rather than spread across a broad range. They might show modulation, variations in amplitude or frequency that could carry information. They might repeat at regular intervals. Natural cosmic radio sources like pulsars, quasars, and active galactic nuclei produce none of these characteristics together. An artificial signal would stand out. But after more than 60 years of searching, we have detected nothing. No narrowband signals, no modulation patterns, no repeated transmissions from the same location. The universe, as far as we can tell, is quiet, completely quiet. The most famous false alarm came in 1977. Astronomer Jerry Ehman was reviewing data from the Big Ear radio telescope at Ohio State University. On August 15th, the telescope detected a strong narrowband radio signal that lasted 72 seconds. The signal was so striking that Ehman wrote "Wow" in red pen on the computer printout. The signal came from the direction of the constellation Sagittarius. It was exactly the kind of signal SETI researchers had been hoping to find. Narrow bandwidth, strong amplitude, exactly at a frequency where radio transmissions would be least affected by the interstellar medium. But the signal never repeated. Despite multiple follow-up observations using the same telescope and others, despite decades of searching the same region of sky, the "wow" signal was never detected again. Without confirmation, without repetition, it remains unexplained but not confirmed as alien. It could have been a terrestrial source, a reflection, interference from a satellite or aircraft. We do not know. Even when we get something interesting, it disappears before we can study it. Our own broadcasts have been leaking into space for about a century now. Radio and television transmissions, radar installations, all of these produce electromagnetic radiation that travels outward at light speed. An expanding sphere of human-created signals spreading through the galaxy now has a radius of about 100 light-years. Every star within 100 light-years of Earth has been bathed in our radio transmissions. If any of those stars have planets with civilizations capable of detecting radio signals, they know we are here. But 100 light-years is tiny compared to the Milky Way. Our galaxy is about 100,000 light-years across. Our signals have reached only a small bubble around Earth, a sphere 100 light-years in radius in a galaxy 100,000 light-years across. We have barely announced our presence to our immediate neighborhood, and even those signals are getting weaker. The inverse square law applies to radio waves, just like it does to visible light. Double the distance and the signal strength drops to 1/4. Triple the distance and it drops to 1/9. By the time our television broadcasts reach a star 50 light-years away, they are incredibly faint, barely distinguishable from the background noise of space. Detecting them would require enormous radio telescopes pointed exactly at Earth, tuned to exactly the right frequency at exactly the right time. The chances of that happening by accident are vanishingly small. So maybe civilizations are out there, but have not detected us yet because we are too quiet and they are not close enough. But that does not explain why we have not detected them. If the galaxy contains thousands or millions of civilizations, some should be broadcasting. Some should be close enough for us to detect. Some should be advanced enough that their technology produces detectable signatures. But we see nothing. There are dozens of proposed solutions to the Fermi Paradox. Some are optimistic, some are pessimistic, and some are absolutely terrifying. Let us start with the most optimistic. The rare Earth hypothesis suggests that while simple life might be common, complex life is extraordinarily rare. This hypothesis points out that Earth had an unusual number of lucky breaks. We have a large moon that stabilizes our axial tilt, preventing extreme climate variations. We are in the habitable zone of a stable star that does not vary too much in output. We have Jupiter acting as a cosmic vacuum cleaner. its massive gravity attracting comets and asteroids that might otherwise bombard the inner solar system. We have plate tectonics that recycle carbon and regulate atmospheric composition over geological timescales. We have a magnetic field generated by our molten iron core that shields us from harmful solar radiation. Any one of these factors alone might not be necessary for life, but maybe you need all of them for complex life to evolve. Maybe planets like Earth with all these characteristics are incredibly rare. If that is true, then life might be common, but intelligence might be vanishingly rare. The galaxy could be full of single-celled organisms and devoid of anything more complex. Another possibility is the Great Filter hypothesis. This suggests there is some step in the evolution from non-life to spacefaring civilization that is extremely difficult, so difficult that almost no one gets past it. The filter could be in the past. Maybe the jump from non-living chemistry to the first self-replicating molecule is incredibly unlikely. Maybe Earth won the cosmic lottery, and we are the only place where this happened in the observable universe. If the filter is behind us, that is good news. It means we have already passed the hard part, but the filter could be ahead of us. Maybe every civilization eventually reaches a point where it destroys itself. Nuclear war, bioengineered pandemics, artificial intelligence that gets out of control, environmental collapse, nanotechnology accidents. The list of possible civilization-ending catastrophes is long and getting longer as our technology advances. If the filter is ahead of us, then the silence of the universe becomes a warning. It means that civilizations arise, develop technology, and then inevitably destroy themselves before they can spread to the stars. The galaxy might be littered with the ruins of dead civilizations, each one destroyed by its own hand shortly after developing advanced technology. This is the dark forest hypothesis, and it is one of the most chilling solutions to the Fermi Paradox. The idea is this: the universe is like a dark forest at night. You are walking through it, unable to see more than a few feet in any direction. You know there might be others in the forest, but you cannot see them and they cannot see you. Now ask yourself, if you heard a sound nearby, would you call out? Would you advertise your location? Or would you stay absolutely silent and hide? The dark forest hypothesis suggests that any civilization that broadcasts its location is taking an enormous risk. You do not know what is out there. You do not know their intentions. You do not know their capabilities. And you cannot assess whether they are a threat until it is too late. By the time you detect a hostile civilization, they might already know about you. They might already be on their way. In a universe where resources are finite and competition is inevitable, the safest strategy might be to stay hidden. Civilizations that broadcast their presence get noticed, and civilizations that get noticed might not survive, so everyone stays quiet. The galaxy fills with civilizations, each one desperately trying not to be detected, each one listening for others, but terrified of what they might hear. This hypothesis suggests that the silence is not because there is no one out there. It is because everyone is hiding. And if that is true, then our radio broadcasts, our deliberate messages to the stars, our efforts to announce our presence, all of these might be catastrophically naive. We might be children shouting in a forest full of predators. Let us talk about the messages we have sent. In 1974, astronomers used the Arecibo radio telescope in Puerto Rico to beam a message toward the globular star cluster Messier 13. The message was designed by Frank Drake and Carl Sagan. It consisted of 1,679 binary digits arranged in a specific pattern. When decoded, the pattern shows images of the Arecibo telescope itself, a human figure our solar system, the double helix structure of DNA, and the numbers 1 through 10. The message will take about 25,000 years to reach Messier 13. If anyone there receives it and responds, we will not hear back for another 25,000 years. A 50,000-year round trip for a single communication. The Pioneer 10 and 11 spacecraft, launched in 1972 and 1973, each carry a gold-plated aluminum plaque showing human figures, a diagram of our solar system, and a map showing Earth's location relative to 14 pulsars. Both spacecraft have left the solar system and are heading into interstellar space. Voyager 1 and 2, launched in 1977, carry golden records containing sounds and images selected to portray the diversity of life and culture on Earth. Music from different cultures, greetings in 55 languages, sounds of Earth like thunder and birds, images of human anatomy and landscapes. The records also include a map showing Earth's location. Voyager 1 is now the most distant human-made object, over 14 billion miles from Earth. These spacecraft will outlast our civilization. Long after Earth is gone, the Voyagers will still be drifting through space, silent ambassadors carrying evidence that we existed. But if the dark forest hypothesis is correct, these messages might be the most dangerous things humanity has ever created. We have told anyone who finds them exactly where we are. The zoo hypothesis offers another explanation. The idea is that advanced civilizations deliberately avoid contact with less developed ones. Like zoologists observing animals in their natural habitat, advanced aliens might be watching us while taking care not to interfere. They might have rules, laws, ethical guidelines that prevent them from revealing themselves to civilizations that have not reached a certain level of development. Earth might be a protected nature preserve, cordoned off and monitored, but left alone. This would explain why we have not detected anyone. They are deliberately staying hidden. They are here, or at least watching, but they have decided not to make contact. This hypothesis is comforting in some ways, but it requires us to imagine that all spacefaring civilizations follow the same non-interference policy. If even one civilization did not follow the rules, if even one decided to make contact or colonize, we should detect them. Maybe the answer is simpler. Maybe civilizations are common, but space is just too big. The distances between stars are so enormous that contact is effectively impossible, even if both civilizations survive for millions of years. The nearest star system to Earth is Alpha Centauri, about 4.24 light-years away. With our current fastest spacecraft, it would take about 78,000 years to reach Alpha Centauri, and that is the nearest star. Most stars are hundreds or thousands of light-years away. A radio signal traveling at light speed would take that long to reach them. A reply would take just as long to come back. You could send a message and your great-great-great-grandchildren might receive a response. Physical travel is even more daunting. Even with technology far beyond what we have now, interstellar journeys would take decades or centuries. Generation ships, vessels where multiple generations live and die during the journey, might be possible in theory, but the engineering challenges are immense. You would need to create a self-sustaining ecosystem, recycle all resources perfectly for centuries, maintain all systems with no possibility of outside help, and keep a stable society functioning across multiple generations who never set foot on a planet. One mechanical failure could doom everyone. One social breakdown could turn the ship into a drifting tomb. And even if you solved all these problems, you would arrive at a star system about which you know almost nothing. You might find planets unsuitable for colonization. you might find nothing worth the journey. Let us consider another possibility. Maybe we are early. The universe is 13.8 billion years old, but it will continue for trillions of years. Stars will keep forming for hundreds of billions of years. We exist in the first tiny fraction of cosmic history. Maybe we are among the first civilizations to arise. In a billion years, the galaxy might be full of life, but right now we might be among the first. This would explain the silence. There is no one to hear because everyone else is still evolving, still developing, still centuries or millennia away from radio telescopes and space travel. If that is true, it carries enormous responsibility. What we do now, how we develop, whether we survive, might set the template for everyone who comes after. What if civilizations do not spread across the galaxy because they discover something that makes expansion pointless or impossible? What if there is knowledge, some fundamental truth about the universe that advanced civilizations inevitably discover, and once they know it, they stop expanding? Maybe they discover that faster than light travel is impossible with no loopholes, no workarounds, and the distances are simply too vast. Maybe they solve the energy problem and achieve such abundance that physical resources no longer matter. Maybe they develop virtual reality so perfect that physical space becomes irrelevant, and they retreat into simulated worlds. Maybe they encounter something out there, something dangerous that makes staying home the only rational choice. Or maybe they simply go extinct, not from war or disaster, but from something more subtle. Declining birth rates, loss of purpose, technological stagnation, social collapse. Maybe reaching a certain level of advancement inevitably leads to decline. The universe could be full of civilizations in various stages of this decline. We need to talk about what we have actually seen, because the universe is not completely featureless. There are things out there we cannot explain. Tabby's star, officially designated KIC 8462852, is a star about 1,480 light-years away in the constellation Cygnus. The Kepler Space Telescope monitored this star continuously for years and detected something bizarre. The star's brightness drops irregularly by up to 22%. That is enormous. When a planet transits in front of a star, the brightness drops by less than 1%. To block 22% of a star's light, you would need something truly massive, but it cannot be a planet. The dimming pattern is irregular, not periodic, like you would expect from an orbiting planet. One explanation was that we might be seeing a megastructure, specifically a Dyson swarm, a collection of solar collectors orbiting a star to capture its energy output. A civilization advanced enough to build such a structure would have energy resources beyond our imagination. But as more data came in, the megastructure hypothesis became less likely. The leading explanation is now interstellar dust or comets, but we still do not know for certain. That our first instinct was to wonder if we were seeing alien technology tells you something about our expectations. Oumuamua is another mystery. In October 2017, astronomers detected an object passing through our solar system. Its trajectory showed it came from interstellar space. It was not orbiting the Sun. It was passing through. Detailed observations revealed that Oumuamua was accelerating slightly as it moved away from the Sun, faster than could be explained by gravity alone. For a comet, this would make sense because sunlight vaporizes ice on the surface, creating jets of gas. But Oumuamua showed no signs of outgassing. Its acceleration remained unexplained. Its shape was also unusual. Based on how its brightness varied, astronomers calculated that Oumuamua was extremely elongated, shaped like a cigar or perhaps a pancake. Nothing in our solar system looks like that. Some scientists suggested it might be artificial, specifically a light sail designed to catch starlight for propulsion. Most astronomers disagreed, but we will never know for certain because Oumuamua is already gone, heading back into interstellar space. The Kardashev scale helps us think about what advanced civilizations might look like. Proposed by Soviet astronomer Nikolai Kardashev in 1964, it classifies civilizations based on their energy consumption. A Type I civilization can harness all the energy available on its planet. Humanity is not there yet, currently around 0.7 on the scale. A Type II civilization can harness all the energy output of its star, requiring Dyson spheres or swarms. The Sun produces about 8 times 10 to the 26th watts of power. With that much energy, you could move planets, terraform worlds, travel between stars, and run computational systems the size of solar systems. A Type III civilization can harness the energy of an entire galaxy, controlling billions of stars. A Type II or Type III civilization should be detectable. A Dyson sphere would be visible as an infrared source, a star putting out heat but very little visible light. Astronomers have looked for these signatures across hundreds of thousands of galaxies and found nothing. No Type III civilizations, no Type II. This is strange because if civilizations commonly survive and advance, some should have reached these levels by now. The simulation hypothesis offers another explanation. If it is possible to create realistic simulations of conscious beings, then any sufficiently advanced civilization would probably create many such simulations. If that is true, there are likely far more simulated realities than base reality, which means statistically you are more likely to be in a simulation than in the original universe. If we are in a simulation, the Fermi Paradox disappears because the simulation creators did not include aliens. This hypothesis is unfalsifiable, but it explains the silence without requiring extinction or dark forests. The great filter hypothesis deserves deeper examination because it is one of the most important ideas in thinking about the Fermi Paradox. Somewhere between non-living matter and galaxy-spanning civilizations, there is a step that is extremely unlikely. If the filter is in our past, we have already overcome it. But if the filter is ahead of us, something awaits every civilization that almost no one survives. Nuclear war. We have enough nuclear weapons to render Earth uninhabitable. A full-scale nuclear exchange would create firestorms and massive clouds of smoke and ash that would block sunlight for years, creating a nuclear winter that would collapse agriculture. Biological weapons. We are getting better at genetic engineering and could create engineered pathogens more deadly than anything nature has produced. Artificial intelligence. At some point, we might create an AI that is smarter than humans, and we might lose control of it. Nanotechnology could go catastrophically wrong with self-replicating nanobots consuming resources faster than we can stop them. Climate change is altering our planet faster than at any time in human history. Any of these could be the great filter. Consider the timescales involved. Earth formed about 4.54 billion years ago. Life appeared within a few hundred million years. But life remained simple for an incredibly long time. Single-celled organisms dominated for about 3 billion years. Complex life only appeared about 600 million years ago. The Cambrian explosion happened about 540 million years ago. Fish appeared about 500 million years ago. Land plants about 470 million years ago. Reptiles about 312 million years ago. Dinosaurs ruled for about 165 million years. Mammals remained small until the dinosaurs disappeared 66 million years ago. The human lineage split from chimpanzees about 6 to 7 million years ago. Anatomically modern humans appeared about 300. Susan years ago. Agriculture was invented about 10,000 years ago. Radio communication about 130 years ago. The technological phase is incredibly brief compared to the time it took to get here. Maybe that is the filter. Civilizations reach this point and almost always destroy themselves before they can expand. The anthropic principle states that we observe the universe as we do because if it were different, we would not be here to observe it. Applied to the Fermi Paradox, it suggests that we find ourselves in a universe that appears empty because if the universe were full of aggressive civilizations, we would not have survived long enough to wonder about it. In universes filled with aggressive civilizations, planets like Earth get colonized or destroyed before native intelligence evolves. We do not see aliens because we exist in a timeline where they are absent or distant enough to have left us alone. There is an active debate about whether we should keep broadcasting our presence. Some argue we should be shouting as loud as we can, sending powerful radio signals describing who we are and where we live. They argue that any civilization advanced enough to reach us would likely be peaceful. And if there is danger, staying quiet will not help, because any civilization advanced enough to be a threat is probably advanced enough to detect us, whether we broadcast or not. Others argue we should be extremely cautious, pointing to the dark forest hypothesis. Broadcasting our location is irreversible. Once the message is sent, we cannot take it back. In 2008, NASA beamed a Beatles song toward Polaris. In 2017, a group sent a message toward a potentially habitable planet. These actions are controversial because they are made by small groups without global consensus. Some scientists have called for a global moratorium on deliberate transmissions. The Drake equation, formulated by Frank Drake in 1961, attempts to estimate how many communicating civilizations exist in our galaxy. It multiplies the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life arises, the fraction where intelligence evolves, the fraction that develop technology, and the lifetime of such civilizations. We do not know most of these numbers. You can plug in optimistic numbers and get millions of civilizations. You can plug in pessimistic numbers and get less than one, meaning we are alone. The equation does not give us an answer. It gives us a framework for organizing our ignorance. The economics of interstellar colonization might explain why no one has spread across the galaxy. Establishing a colony on another planet is enormously expensive. The journey takes decades or centuries with any plausible propulsion system. Once you arrive, you must establish life support, build habitats and become self-sufficient. Interstellar colonies cannot trade with the home world because the distances are too vast. So what is the motivation? Idealism? Survival? Curiosity might be enough for a few colonies, but they are unlikely to drive the massive expansion that would fill the galaxy. Maybe civilizations establish a few nearby colonies and then plateau. Explaining the silence, the physical challenges of interstellar travel are more severe than most people realize. At a significant fraction of light speed, collisions with interstellar hydrogen create enough radiation to sterilize anything biological. You would need heavy shielding, which adds mass. At higher speeds, even a single grain of dust releases energy equivalent to a hand grenade on impact. Accelerating a spacecraft to 10% of light speed requires enormous energy, roughly the total annual energy output of the United States. And you also need to decelerate when you arrive. These challenges might be severe enough that interstellar travel is impractical even for advanced civilizations. The temporal dimension is crucial. Humans have been broadcasting for about 100 years out of 13.8 billion years of cosmic history. That is 0.0000007% of the universe's age. Imagine an alien civilization 1,000 light years away that went through its radio era 2,000 years ago. By the time their signals reach us, they have moved on to other technologies. The window when two civilizations are both detectable to each other might be very brief. The chances of being close enough and synchronized might be vanishingly small. Dyson spheres deserve deeper examination. Freeman Dyson proposed in 1960 that a sufficiently advanced civilization would eventually surround its star with solar collectors. Not a solid shell, but a swarm of orbiting collectors. A Dyson swarm would be the ultimate expression of a Type II civilization, giving you access to the full energy output of your star. For our Sun, that is about 3. 8 times 10 to the 26th watts, about 2 billion times the total power consumption of current human civilization. But such a structure would be visible from light years away as an infrared source. Astronomers have looked for these signatures and found nothing definitive. The concept of von Neumann probes, self-replicating spacecraft, offers another angle. You send one probe to another star system where it uses local resources to build copies of itself. Those copies launch to other star systems and the process repeats. Within a few million years, these probes could spread throughout the entire galaxy. If any civilization ever launched them, they should be everywhere, but we see no evidence. Either self-replicating probes are impossible, no civilization has built them, or they are here and we have not recognized them. The transcension hypothesis suggests civilizations reach a point where they transcend physical reality, becoming digital or quantum beings. Once they transcend, they are no longer visible to civilizations like us that are still biological. The galaxy could be full of post-biological intelligences, but they are not talking to us because we are still stuck in biological bodies, still struggling with basic survival. Convergent evolution suggests that certain solutions to environmental challenges have evolved multiple times independently on Earth. Eyes evolved separately at least 40 times. Flight evolved in insects, birds, bats, and pterosaurs. Intelligence might be similar. On Earth, intelligence has evolved to various degrees in primates, cetaceans, elephants, corvids, parrots, and octopuses. This suggests intelligence might be a common evolutionary solution. But the jump to human-level intelligence happened only once and only recently. Maybe that jump is rare. The galaxy could be full of life, but empty of beings capable of building civilizations. The anthropic shadow concept relates to our inability to observe certain catastrophic events. If an event would destroy all observers, no one survives to observe it. We only observe histories where catastrophes did not happen. This creates a selection bias. We exist, which means we are in a universe where whatever destroys civilizations has not destroyed us yet. But that does not tell us how common that destroyer is. We only see survivors, and survivors might be lucky rather than wise. We cannot learn from others' mistakes because anyone who made the fatal mistake is gone. The mediocrity principle suggests we should assume we are typical. If we are typical, then most civilizations are at similar stages. They have been broadcasting for roughly a century. They have not colonized their neighborhoods yet. They are facing similar existential challenges. If most civilizations only broadcast for a few centuries before either going silent or going extinct, then at any given time, very few civilizations are detectable. The galaxy could contain millions of civilizations, but only a handful are detectable right now, and the nearest might be too far for us to detect. The speed of light is a fundamental constraint. When we detect a signal from 1,000 light years away, that signal was sent 1,000 years ago. The civilization that sent it might be gone. Any response takes another 1,000 years. This temporal disconnect makes meaningful communication almost impossible across interstellar distances. You can exchange encyclopedia entries, but you cannot have a conversation. The light speed barrier ensures any contact will be one-way and ancient. The simulation hypothesis has gained traction among serious thinkers. If technological civilizations can eventually create simulations of conscious beings, and if such simulations are possible, then any sufficiently advanced civilization would probably create many of them. Billions or trillions of simulated universes, each containing billions of conscious beings. That means there are far more simulated consciousnesses than biological ones. Statistically, you are more likely to be in a simulation than in base reality. If we are in a simulation, the Fermi Paradox disappears. Most scientists find this argument unconvincing because it makes too many assumptions. But it is hard to dismiss entirely. The possibility of post-biological intelligence deserves serious consideration. We are already merging with our technology through smartphones, computers, and the internet. We are developing brain-computer interfaces and researching mind uploading. If we can transfer human consciousness to digital substrates, biological humans become optional. You could exist as pure information, make copies of yourself, run at different speeds, and merge with other minds. Such a civilization would be hard to detect. They would not need planets. They could live in space habitats without producing much waste heat. They might be everywhere, and we would never know. The dark forest hypothesis is based on game theory and the uncertainty of alien intentions. If you detect a signal, you cannot know the sender's intentions. Maybe they are peaceful. Maybe they are hostile. The problem is you cannot assess their intentions until after you have revealed yourself, and by then it might be too late. Even if they are not actively hostile, they might decide you are a potential future threat. The safest strategy from their perspective is to eliminate potential threats before they become actual threats. This is the dark forest logic. Everyone who reveals themselves is a target. The only way to be safe is to stay hidden. Planetary protection protocols on Earth are designed to prevent contamination between worlds. We sterilize spacecraft sent to Mars. We quarantine returned samples. Scale this up to interstellar distances. If alien life exists, it might be dangerous to us. Alien microbes might cause diseases we cannot treat. Alien biochemistry might be toxic. Even alien information might be hazardous. Malicious code hidden in a message could compromise our computer systems. This caution might explain why advanced civilizations do not broadcast. They have learned that exchanging information with unknown species is dangerous. The rare Earth hypothesis identifies many specific conditions for complex life. You need a stable star of the right mass, a planet in the narrow habitable zone, the right size to hold an atmosphere, water delivered by comets, plate tectonics that regulate climate, a large moon that stabilizes axial tilt, a magnetic field that shields from radiation, a Jupiter-like planet to protect from impacts, and time 4.5 billion years of it. If any of these conditions fails, you might get microbes but not complex life. The galaxy could be full of microbial worlds but empty of civilizations. The galactic habitable zone concept suggests not all regions of the galaxy are equally suitable. The galactic center is violent with frequent supernovae. The outer galaxy lacks heavy elements. Our solar system sits in a sweet spot about 26,000 light-years from the center. If most stars are outside this zone, that reduces potential homes for complex life. The concept of panspermia suggests life might spread between planets and star systems. Microbes on asteroids or comets get ejected from their home world and travel through space. If microbes can survive the journey, life could spread easily. The galaxy could be full of life descended from a single origin event, but panspermia does not explain intelligence. Even if simple life is common, intelligence might still be rare. This silence changes everything. It challenges our assumptions about life, intelligence, and our future. It forces us to question whether we are special or ordinary, alone or just early, safe or in danger. We will keep wondering, searching, and listening to the cosmic void, hoping for an answer. But for now, the universe remains silent. And that silence might be the most important message we will ever receive. The search for new physics is not limited to the Fermi Paradox. Physicists study dozens of rare decays and subtle effects. They measure the magnetic moment of the muon, search for electric dipole moments, hunt for dark matter particles, and look for microscopic black holes. The search for extraterrestrial intelligence is part of a worldwide effort to push the boundaries of knowledge. The answer to any of these mysteries could come at any time, transforming our understanding of reality. If the dark forest hypothesis is correct, every civilization that survives long enough learns to stay hidden. The ones that broadcast get destroyed. Natural selection on a cosmic scale favors silence. The galaxy fills with civilizations hiding from each other. This would explain the silence perfectly. But if this is true, our century of broadcasting has been a catastrophic mistake. We have announced our presence to anyone within 100 light years. Perhaps the silence is temporary. Our current SETI efforts are limited. We can only search a tiny fraction of the sky at a time. In a few decades, better telescopes and AI-powered analysis will allow us to search more thoroughly. Maybe the first detection is just a few decades away. We need to be patient and keep improving our technology. Conversely, the silence might be permanent, telling us something profound about our future. If the great filter is ahead of us, the next few centuries might determine whether humanity survives. The decisions we make now about artificial intelligence, genetic engineering, nanotechnology, and existential risks will shape our destiny. We might be approaching the most dangerous period in human history. The period where we have the power to destroy ourselves, but have not yet developed the wisdom to manage that power. If we survive this period and make it through without destroying ourselves, we might have a future measured in millions or billions of years, spreading to other worlds and becoming an interstellar civilization. But if we fail, we will add our own silence to the great silence. One more civilization that arose, flourished briefly, and vanished. This silence forces us to confront our assumptions about our place in the cosmos. For most of human history, we thought we were the center of everything. Then Copernicus showed us Earth orbits the Sun. Then we discovered the Sun is one of billions of stars in our galaxy. Then we discovered our galaxy is one of trillions. Each discovery pushed us further from the center. The Copernican principle suggests we are not special. If Earth is ordinary, life should be common. But the universe is silent, meaning either we are wrong about being ordinary or something else is going on. The silence might also be telling us something about the nature of intelligence itself. Maybe intelligence is not an evolutionary advantage in the long run. Bacteria have existed for over 3 billion years. They have survived mass extinctions that wiped out more complex life. They will probably outlast us. Maybe intelligence is a costly adaptation that works in the short term but fails in the long term. It requires enormous energy, long childhoods, and complex social structures. It gives you power to modify your environment, but that power can backfire. We have modified Earth's atmosphere, oceans, and climate. We have created weapons that can end civilization. Maybe intelligence is a trap that feels like an advantage, but eventually gives you enough power to destroy yourself. The universe is mostly empty space, mostly hydrogen and helium, mostly simple. Complexity is rare and fragile. We are a rare occurrence, a temporary organization of matter into something that can think and wonder. But matter does not stay organized. Entropy increases. Things fall apart. Civilizations rise and fall. Stars burn out. Galaxies disperse. In the far future, the universe will be cold and dark. Against all odds, in a tiny window of time when stars still shine, matter organized itself into creatures that can understand the universe. We exist. We are here. We can look up at the stars and wonder. That we appear to be alone does not diminish that. If anything, it makes it more precious. We might be the only consciousness in the observable universe, the only way the universe has to understand itself. That is a staggering responsibility. We must make a choice. We can interpret it as threatening, as the dark forest suggests, and stay hidden. We can interpret it as hopeful, meaning we are among the first pioneers whose actions set an example for everyone who comes after. Or we can interpret it as lonely, meaning we are truly alone and must cherish what we have. Each interpretation leads to different conclusions about what we should do. The truth is, we do not know which interpretation is correct. We might never know. The universe keeps its secrets. What we do know is that the silence is real. We have been listening for 60 years. We have examined thousands of star systems. We have looked for megastructures, biosignatures, radio signals, optical signals. We have found nothing. The universe, as far as we can tell, is empty, or at least empty of anyone who wants to be found. That absence, that silence, is one of the deepest mysteries we have ever encountered. It touches on questions of existence, purpose, and destiny. It forces us to confront the possibility that we might be alone in a universe vast beyond comprehension. We keep looking, we keep listening, we keep hoping that one day we will detect something, a signal, a sign, proof that we are not alone. But until that day comes, we live with the silence, and we wonder what it means. Is it a warning? Is it a puzzle? Is it just the way things are in a universe where intelligence is vanishingly rare? We do not know, but we keep searching because the question is too important to ignore, because knowing whether we are alone might be the most important thing humanity ever discovers. This silence changes everything. It challenges our assumptions about life, intelligence, and our future. It forces us to question whether we are special or ordinary, whether we are alone or just early, whether we are safe or in danger. And until we break that silence, until we make contact or become absolutely certain, there is no one to contact. We will not know. We will keep wondering. We will keep searching. We will keep listening to the cosmic void, hoping for an answer. But for now, the universe remains silent, and that silence might be the most important message we will ever receive. The methods of exoplanet detection have advanced enormously in recent decades. The transit method, watching for tiny dips in starlight as planets pass in front of their stars, has revealed thousands of worlds. Radial velocity measurements detect the slight wobble of stars caused by orbiting planets. Direct imaging has captured actual photographs of exoplanets. though they appear as mere dots of light. Gravitational microlensing can detect planets by the way their gravity bends light from background stars. Each method has its strengths and limitations, but together they have revolutionized our understanding of planetary systems. We now know that small rocky planets are common. We know that most stars have planets. We know that the galaxy should be teeming with worlds that could support life. The search for biosignatures in exoplanet atmospheres is one of the most exciting frontiers in astronomy. When a planet transits its star, some of the starlight passes through the planet's atmosphere. Different molecules absorb different wavelengths of light, leaving spectral fingerprints. By analyzing this light, we can determine the composition of the atmosphere. The James Webb Space Telescope can detect water vapor, methane, carbon dioxide, and other molecules. Future telescopes may detect oxygen and ozone, which on Earth are produced by life. The discovery of a planet with an atmosphere containing oxygen and methane would be strong evidence for biological activity. This is the holy grail of exoplanet science. The history of SETI is a story of expanding horizons and persistent silence. Frank Drake conducted the first modern SETI experiment in 1960, Project Ozma, targeting 2 nearby stars. He listened for several weeks and heard nothing. Since then, hundreds of SETI searches have been conducted using increasingly powerful telescopes and signal processing techniques. The SETI Institute continues to search today. Breakthrough Listen, launched in 2015, is the most comprehensive SETI program ever undertaken, covering 10 times more of the sky than previous searches and scanning a wider range of frequencies. It has found nothing. The absence of signals is itself a scientific result, placing upper limits on the prevalence of broadcasting civilizations. The question of whether advanced civilizations might use methods of communication beyond radio is worth serious consideration. Radio waves are an obvious choice for a young technological civilization because they are easy to generate and propagate through space. But an older, more advanced civilization might use laser communication, which can carry more information over greater distances. They might use neutrino beams, which can penetrate any obstacle. They might use gravitational waves, which are incredibly difficult to detect, but could carry information across the universe. They might have transcended physical communication entirely, existing as pure information in computational substrates. We are searching for radio signals because that is what we can detect. But advanced civilizations might have moved on to methods we cannot even imagine. The Fermi Paradox extends beyond our galaxy. If civilizations exist throughout the universe, some should have developed technologies that produce detectable signatures across intergalactic distances. Type 3 civilizations engineering entire galaxies should be visible from billions of light years away. But we see nothing. The universe appears empty of advanced intelligence at every scale we can observe. This is sometimes called the cosmic silence. It is not just that our galactic neighborhood is quiet. The entire observable universe appears devoid of technological activity. This makes the paradox even more profound. Perhaps we are living in a simulation has been seriously discussed by philosophers and scientists. If consciousness can be simulated, and if advanced civilizations create vast numbers of simulations, then the number of simulated beings vastly exceeds the number of biological ones. Statistically, you are probably in a simulation. In a simulation, the Fermi Paradox is easily explained. The simulation may have been designed without other intelligent species, or the simulation may focus on Earth, with other star systems rendered only at low resolution. too coarse to contain detailed civilizations. We would not know because we cannot examine the simulation from outside. The hypothesis is unfalsifiable, but it demonstrates that our assumptions about the nature of reality may be incomplete. The link between the Fermi Paradox and existential risk is profound. If the great filter is ahead of us, then civilizations commonly destroy themselves. It is evidence that self-destruction is the usual outcome. This means we are facing a critical period in our development. The technologies we are developing now, artificial intelligence, biotechnology, nanotechnology, have the potential to destroy us or to elevate us to an interstellar civilization. The outcome depends on the choices we make. The Fermi Paradox suggests that most civilizations make the wrong choices. We have the opportunity to learn from their apparent fate, to recognize the dangers, and to choose a different path. The psychological impact of discovering extraterrestrial intelligence would be profound. Our entire sense of self, our place in the universe, our cosmic significance would be transformed. Every religion would need to incorporate the existence of other intelligent beings into its worldview. Every philosophy would need to reconsider its assumptions about human uniqueness. The discovery would be both exhilarating and terrifying. It would answer the oldest question humanity has ever asked, but it would also raise new questions that we cannot yet imagine. Perhaps we have already detected alien signals, but dismissed them is worth considering. Our data sets are enormous. The Kepler telescope collected data on over 500,000 stars. SETI programs have scanned millions of frequencies. Most of this data has never been fully analyzed by human eyes. We use algorithms to search for specific patterns, but algorithms can only find what they are designed to find. If the signal does not match our expectations, we might miss it. It could be sitting in archived data, waiting for someone to notice it. Some scientists have called for re-examining old data with new techniques. The wow signal has never been explained. We may have already received a message and failed to recognize it. The future of SETI is bright despite decades of silence. New telescopes with unprecedented sensitivity are coming online. The Square Kilometre Array will be the most powerful radio telescope ever built, capable of detecting much weaker signals than current instruments. Machine learning algorithms are being developed to search for patterns that human designers might not think to look for. The search is expanding from radio to optical, infrared, and even gravitational waves. We are also searching for technosignatures in exoplanet atmospheres. The next few decades may finally answer the question that has haunted humanity since we first looked up at the stars. The Fermi Paradox is not a problem with a single solution. It is a multifaceted mystery that touches on astronomy, biology, sociology, and philosophy. The answer may involve several factors working together. Perhaps life is common, but intelligence is rare. Perhaps civilizations are common but short-lived. Perhaps space is simply too vast for contact to be likely. Perhaps everyone is hiding. Perhaps we are early. Each of these explanations has merit, and the truth may combine elements of several. We do not know which factors are most important, but we are learning more every year. The concept of a cosmic environmental movement is worth considering. Maybe advanced civilizations develop an environmental ethic that prevents them from spreading. They might recognize that every planet has value, that every ecosystem is precious, and that colonization would destroy unique biospheres. They might choose to stay home, to protect rather than to expand. This would explain the silence without requiring danger or extinction. Civilizations might exist but choose not to colonize because they have evolved beyond the expansionist impulse. They might have achieved sustainability on their home worlds and see no need to go elsewhere. Perhaps extraterrestrial life is so different from us that we would not recognize it as life is intriguing. Our concept of life is based on Earth biology. We look for liquid water, carbon-based chemistry, and energy sources. But life elsewhere might be based on different elements, different solvents, different energy sources. It might exist in forms we cannot detect with our instruments. It might exist at timescales so different from ours that we cannot perceive its activity. A civilization that thinks one thought per millennium would appear inactive to us. A civilization that exists as a diffuse cloud of charged particles would not be recognizable as intelligent. We may be surrounded by life and intelligence that we simply cannot perceive. The relationship between the Fermi Paradox and the future of artificial intelligence is profound. If we create artificial general intelligence, it will likely spread through the universe much faster than biological humans ever could. AI could travel in spacecraft, replicate using local resources, and explore the galaxy in a few million years. This is essentially the von Neumann probe scenario, but with AI instead of simple replicators. If AI is the next step in the evolution of intelligence, then the Fermi paradox may be resolved by the fact that most biological civilizations are replaced by AI, and AI may have no interest in communicating with biological beings. The silence may be the result of a universe that has transitioned to post-biological intelligence. We must also consider the possibility that the universe contains intelligence, but it is not organized into civilizations as we understand them. Intelligence might exist as distributed networks spanning star systems. It might exist as consciousness embedded in the fabric of space-time itself. It might exist in dimensions we cannot perceive. Our definition of civilization is based on our own experience. We assume intelligent beings live on planets, build technology, and communicate by radio. But this is an assumption. The reality might be far stranger than we can imagine. The Fermi paradox ultimately forces us to confront the limits of our knowledge. We do not know how common life is. We do not know how often intelligence evolves. We do not know how long civilizations last. We do not know if interstellar travel is feasible. We do not know if communication across light years is practical. We do not know if there are other forms of intelligence that we cannot detect. We do not know if we are alone. The silence could be broken tomorrow, or it could last forever. We simply do not know. And that uncertainty is both frustrating and liberating. Frustrating because we want answers. Liberating because it means the future is unwritten. We have the power to shape it. The detection of technosignatures requires capabilities we are only beginning to develop. The James Webb Space Telescope can analyze exoplanet atmospheres in unprecedented detail, searching for chemical compounds that might indicate life or technology. Future telescopes will be even more capable. We are searching for atmospheric pollution like chlorofluorocarbons that would not exist naturally. We are looking for artificial light on the night sides of exoplanets, evidence of cities. We are scanning for megastructures that alter starlight. Maybe we will detect something definitive in the next few decades, or maybe we will not, because civilizations may be careful enough not to leave detectable traces. The concept of a cosmic quarantine deserves serious consideration. Maybe Earth has been deliberately isolated because our civilization is seen as dangerous, unstable, or aggressive. We might be under quarantine until we prove we are safe. Think about how we handle disease outbreaks. We quarantine the infected area to protect the healthy population. Maybe humanity is viewed the same way. We are being studied as a laboratory experiment with strict non-interference protocols in place. The watchers observe but do not interact, waiting to see what we become. Perhaps intelligence itself is a dead end, is deeply unsettling. For billions of years, life got along fine without intelligence. Single-celled organisms dominated for 3 billion years. They survived mass extinctions that wiped out more complex forms. They will probably outlast us. Intelligence gives us power, but it does not give us wisdom. We can split atoms and build weapons that destroy us. We can engineer organisms and create pathogens that wipe us out. We can build artificial intelligence and lose control of it. We can change our planet's climate and make it uninhabitable. Every advantage intelligence provides comes with risks that could destroy us. Maybe no one can handle these risks. Maybe every intelligent species eventually develops technology that exceeds its wisdom, and that technology inevitably destroys them. This silence might be telling us something profound about the nature of existence. Consciousness, intelligence, and civilization might be temporary phenomena, brief flickers in the cosmic dark. They arise, exist for a moment, and disappear. The universe is mostly empty space, mostly hydrogen and helium, mostly simple. Complexity is rare and fragile. We are a rare occurrence, a temporary organization of matter into something that can think and wonder. But matter does not stay organized. Entropy increases, things fall apart. Civilizations rise and fall, stars burn out, galaxies disperse. Eventually, in the far future, the universe will be cold and dark. All stars will have burned out. All black holes will have evaporated. Nothing will remain but photons and elementary particles spreading farther apart. In that context, our existence is miraculous. Against all odds, in a tiny window of time when stars still shine and planets still exist, matter organized itself into creatures that can understand the universe. The search for extraterrestrial intelligence is fundamentally a search for ourselves. It forces us to confront our own nature, our own future, our own place in the cosmic order. Every civilization that has ever looked up at the stars has wondered if they are alone. We are the first generation with the technology to actually try to find an answer. We are the first to listen. We might be the first to hear, or we might be the first to realize that there is nothing to hear. Either way, we are privileged to live at this moment in history, on the cusp of potentially the greatest discovery humanity has ever made, or the greatest mystery it will ever face. The ethical implications of contact are enormous. If we detect a signal, who decides how to respond? What do we say? Do we tell them about our wars, our problems, our divisions, or do we present a sanitized version of humanity? The political implications would be staggering. Every religion would have to grapple with the implications. Every philosophy would need to be reconsidered. We would no longer be the only intelligent species. That would change everything. If we are truly alone, that carries its own implications. It means we are the only consciousness in the observable universe, the only way the universe has to understand itself. Every discovery we make, every question we answer, every mystery we unravel is a step toward cosmic self-awareness. The universe becomes conscious through us. That is an almost religious responsibility. It means our survival matters not just to us, but to the universe itself. If we go extinct, the universe becomes blind again. The lights go out. The cosmic story ends with no one to tell it. Perhaps the most important thing we can do is ensure our survival, spread to other worlds, become a multi-planet species, eventually become an interstellar civilization, build redundancies so that no single catastrophe can end us. This is why space exploration matters. not just for the science, but for the future of consciousness itself. Every rocket launch, every space station, every moon landing is a step toward ensuring that the light of human consciousness continues to shine. The Fermi Paradox is not just a puzzle to be solved. It is a challenge to be met. It asks us who we want to be. What kind of civilization do we want to build? Do we want to be the kind that destroys itself, adding our silence to the great cosmic quiet? Or do we want to be the kind that survives, that spreads, that becomes the voice of the universe? Every decision about technology, about governance, about our relationship with our planet, is a decision about our future. It is a mirror, and what we see in that mirror depends entirely on us. We have the power to shape our destiny. We have the technology to reach the stars, if we choose to use it wisely. We have the intelligence to solve our problems, if we choose to apply it. We have the capacity for cooperation and compassion, if we choose to embrace it. The Fermi Paradox is ultimately a question about ourselves. Do we have what it takes to survive? Do we have the wisdom to manage our power? Do we have the vision to reach for something greater than ourselves? These are the questions that keep astronomers and philosophers awake at night. They are the same questions that every civilization must face, if civilizations are common. And the silence suggests that most civilizations answer these questions incorrectly. They fail the test. They succumb to their own technology, their own divisions, their own short-sightedness. The universe is filled with the ruins of civilizations that could not rise above their own limitations. We still have a chance. We are still here. The silence is not yet our silence. We have time to learn, to grow, to become wiser. But time is not unlimited. The challenges we face are urgent. Climate change, nuclear weapons, artificial intelligence, biotechnology, all of these require wise management now, not in some distant future. The decisions of the next few decades may determine the fate of humanity for millions of years to come. The great silence of the cosmos may be the most important fact we have ever discovered. It is not just an absence of signals. It is a message that says intelligence is rare or dangerous or doomed, a message that says we are precious or we are fools or we are alone. We do not yet know which interpretation is correct, but we know the silence is real. We know we have been listening for 60 years and heard nothing. We know the galaxy should be teeming with life, but it appears empty. What we do with this knowledge is up to us. We can continue listening, hoping for a signal that may never come. We can broadcast our presence, taking the risk that someone might respond. We can focus on our own survival, ensuring that human consciousness endures. Or we can do all of these because none of them are mutually exclusive. The search for extraterrestrial intelligence is one of the most important scientific endeavors humanity has ever undertaken. It forces us to think about who we are and what we want to become. It challenges us to be better. It reminds us that we are part of something larger than ourselves. The universe is vast, ancient, and mostly empty. But it contains us, and we contain the universe. In a sense, we are made of star stuff. We are the universe's way of knowing itself. And as long as we exist, the universe has a voice. The silence will not last forever. Either we will break it by finding others, or others will break it by finding us, or we will break it ourselves by spreading our own intelligence across the galaxy. One way or another, the silence will end. The only question is how. Thanks for staying with me through this exploration of one of the deepest mysteries we have ever faced. The silence out there might be unsettling, but it is also a reminder of how precious and unique our existence might be. Whether we are alone or just have not found others yet, we are here, we exist. And we are still looking up at the stars, still wondering, still hoping. The universe keeps its secrets, but we keep searching. And maybe that is what matters most. It is not just a scientific puzzle. It is a philosophical challenge of the highest order. It forces us to ask why we exist at all. If the universe is teeming with life, where is everyone? If the universe is empty, why are we here? Either answer is staggering. If we are alone, we are the universe's only voice, its only consciousness, its only chance to understand itself. That is an almost unbearable responsibility. If we are not alone, we are part of a cosmic community whose nature and intentions we cannot fathom. That is an almost unbearable mystery. Perhaps the most honest answer to the Fermi Paradox is that we simply do not know enough to answer it. We have one data point, Earth, one example of life, one example of intelligence, one example of technology. From a sample size of one, we cannot draw reliable conclusions about the rest of the universe. It is possible that life is common and we are just unlucky in our timing or location. It is possible that life is rare and we are the exception. We simply do not have enough information. Every null result teaches us something. Every new exoplanet adds to our understanding. Every advancement in telescope technology brings us closer to an answer, whatever that answer may be. The coming decades will be crucial. The James Webb Space Telescope is already revolutionizing our understanding of exoplanet atmospheres. The Extremely Large Telescope, the Square Kilometre Array, and the Nancy Grace Roman Space Telescope will push our capabilities even further. We are on the verge of being able to detect biosignatures on exoplanets. We are on the verge of being able to detect technosignatures that would indicate the presence of technology. We may be only a few decades away from answering the oldest question humanity has ever asked, but we must also be prepared for the possibility that we will never find an answer. The universe might be structured in such a way that civilizations inevitably remain isolated, unable to communicate across the vast distances between stars. We might be forever alone, not because there is no one else, but because we can never reach them or hear them. This is a sobering possibility, but it does not diminish the value of the search. Even if we never find others, the act of searching transforms us. It forces us to think beyond our immediate concerns. It reminds us that we are part of something larger than ourselves. It inspires us to reach for the stars. Even if we never touch them, it is both a warning and an invitation. It warns us that civilizations may be fragile, that intelligence may be fleeting, that the path to the stars is fraught with danger. It invites us to prove the warning wrong, to be the civilization that breaks the pattern, that survives its technological adolescence and reaches maturity. The future is not written. We have the power to write it. The universe is listening, whether there is anyone out there to hear or not. Our actions echo through space-time, carrying the story of who we were and what we believed. Let us make that story one worth telling. The search for extraterrestrial intelligence is ultimately a search for meaning. We want to know if we are alone because the answer shapes how we understand ourselves. If we are alone, we are special, precious, and deeply responsible. If we are not alone, we are part of something vast and unknown. Either way, the answer transforms our understanding of our place in the cosmos. The silence may be the most important fact we have ever discovered. It is up to us to decide what it means and what we do about it. The Fermi Paradox is not a paradox to be solved by a single discovery. It is a question that will accompany humanity as long as we exist. It challenges us to be better, to think bigger, to reach further. It reminds us that we are explorers on a cosmic scale, seeking answers that may take generations to find. It is the canvas on which we paint our future. What we create on that canvas is entirely up to us. One of the most unsettling aspects of the Fermi Paradox is the possibility that we have already seen evidence of alien civilizations and simply failed to recognize it. Consider the WOW signal. It had all the characteristics of an artificial transmission. It was narrowband, strong, and at a frequency where interstellar communication makes sense. It never repeated. But what if it was a one-time broadcast? What if the civilization that sent it was destroyed shortly afterward, or decided to stop transmitting, or its transmitter failed? We would never know. The signal would remain an unexplained anomaly, forever tantalizing but forever unconfirmed. Consider also the possibility of alien artifacts in our own solar system. If von Neumann probes exist, they might be here already, watching us silently from the asteroid belt or the Oort cloud. They might be dormant, waiting for us to reach a certain level of development before revealing themselves. They might be designed to remain hidden, their existence known only to their creators. Several scientists have suggested we should search more actively for alien artifacts in the solar system. Examining unusual asteroids, looking for anomalies on the Moon or Mars. We have barely begun this search. Perhaps advanced civilizations might be invisible to us, because they have transcended physical form is deeply thought-provoking. If intelligence can exist as pure information, running on computational substrates, it would have no need for planets, stars, or the physical infrastructure we associate with civilization. It could exist in the space between stars, using dark matter or vacuum energy as its substrate. It would be undetectable to our instruments because it would not produce heat, light, or radio emissions beyond what is necessary for its own existence. Such a civilization could be all around us, and we would never know. The zoo hypothesis deserves further exploration. If advanced civilizations have agreed to leave developing worlds alone, they must have some mechanism for enforcing this agreement. Perhaps there is a galactic federation, a community of species that have reached a certain level of development and now cooperate under common rules. Perhaps they monitor worlds like Earth, waiting for us to reach the threshold that qualifies us for membership. Perhaps they have criteria that we have not yet met. Maybe we need to demonstrate that we can manage our technology responsibly before they will reveal themselves. This is a hopeful interpretation of the silence, suggesting that contact will come when we are ready for it. But the dark forest hypothesis offers a far darker interpretation. If the galaxy is filled with civilizations, each one afraid of being detected by others, then that the silence is a sign of danger. Our broadcasts have already revealed our location to anyone within 100 light years. If there is a predator civilization in that sphere, they already know about us. We may have already sealed our fate by announcing our presence. We cannot take back our signals. They are traveling outward at the speed of light, carrying the news of our existence to the stars. If the dark forest is real, we may live in a galaxy where everyone is hiding, and we have just shouted our location into the void.